Assalamu alaikum. Hi everyone. In today's video, we are going to break down the fundamentals of mathematical optimization and walk through how to solve a complex problem using standard industry tools. Whether you are a student or an engineer, understanding how to structure these problems is key to finding the best solution in any system. The general form is this. If x is the objective function, where hi is the equality constraint, and another type of constraints, gj, inequality constraints. M is the number of equality constraints, and there could be R number of inequality constraints. In addition, there is special type of constraints called bounds. These are allowable values of x. These constraints can also be written as a general inequality constraints because it has inequality symbols, and to write bounds as inequality constraints, we can simply rearrange it and we will get this. If we write x less than equal x u, we could write also minus x less or equal x minus xl. X is the variable that has to be optimized, which is the decision variable. Depending on the type of f, h, and g, we can classify the optimization problem to LP, linear programming problem, where the objective function and all its constraints are linear. We can mention also to find the maximum of a function is equivalent to find the minimum of minus f. We can write isn't. So to find the maximum of fx is equivalent to find the minimum of minus f of x. The second type we encounter is the quadratic programming, QP. In a QP problem, the objective function is quadratic, meaning it contains square terms while the constraints remain linear. A standard QP objective function is usually written in terms in the form of this, where H represents the Hessian matrix of a quadratic term and C represents the linear coefficients. Here is an example of 6-variable optimization problem where the goal is to maximize a function J involving variables x1 through x6. This problem isn't just a free-for-all. It is subject to linear equality constraints such x3, x4, x5, x6, and variable bounds, where each variable has a minimum and maximum limit, such as x3 being capped to 24,000. Because most solvers are designed to minimize a function, We actually solve this by minimizing the negative of J. This is the form that qpOASES solver accepts. The objective is the same as the standard QP form. However, it uses a general form for both the equality and equality constraints, which is these equations. Now the question can be, if it has only inequality constraints, how do we include the equality constraints? For equality constraints, we can write this. This is the equivalent linear equality constraints equation. These two expressions are the same. We should rearrange also our problem in this form. If you are using MATLAB, you can use qpOASES solver, which uses an online active set strategy. The process follows 5 clear steps. Define the Hessian matrix and the gradient G, which is C here, C transpose. You will create a 6 by 6 matrix for this problem for H and C vector for linear terms. Now set up the linear equality constraints. Define your equality constraint in a matrix A. The inequality constraints such this equation. Set bounds, establish your lower and upper limits. Now we have all the matrices H, C, A, B, X, L, X, U, and we can download qpOASES from GitHub, which is qpOASES master. After unzip it, we go to interface, and here is MATLAB. We copy this path and go to MATLAB and put it here. After doing this, we can see which compiler of C or C++ we have by writing this mix setup C, and we can choose between two. Here is Microsoft Visual C++ 2022 and the other compiler. Mix configured to use Microsoft Visual C++. Also, we can verify for C++. Also, we can use Visual C++. We can compile the code, which is written by C++. By writing make the program. Now we get this executable file for the qpOASES, so we can use it in MATLAB. I will open new script. Here I wrote the code for MATLAB. We define each matrix. We put H as sparse matrix to be convenient with the program, and define C, A matrix, and also a sparse matrix. Now we will run this code. And we will get the optimal value of X. Here is the iteration, lambda, exit flag. Here are the value of X, the optimal value of X. We can also use quadprog function in MATLAB, but here we will give the initial value of X. We'll get the same result. This is the same result for x1, x2, x3, 4, 5, 6. Having previously formulated the quadratic programming QP problem, our focus now shifts to solving this mathematical challenge using Simulink and the QPA SCS solver. Our objective is to determine the optimal values for the 6 decision variables, x1 through x6, to maximize the profit derived from the operation, while respecting all underlying process constraints. Recall that we formulated our objective functions and constraints into the standard form required by the QPA SCS solver, which utilize the Hessian matrix H, the linear term coefficients vector C, general constraint matrices AB, and bonds XL, XU. We first go to qpOASES interface Simulink. Then we make this C++ file. This will be an S function in Simulink. This will create this S function we will use later in Simulink. First, we will open a blank Simulink model, Simulink. Create. We will create a core component which we can call the QP problem formulation block. This block will define and pass out all the necessary matrix and vector data for the solver. We implement this formulation using MATLAB function block found under the user-defined functions in the library browser. We'll drag and drop, double click. Since this function only generates the required inputs for the solver, it will not need any internal input fields. Instead, it will output the 6 required matrices vectors. Here I wrote this function. There is no input, only outputs. we define H matrix C, A, B, XL, XH. There is something I forget to mention. Here in the qpOASES file, C++ file, we define the sampling time 0.1 and the number of control inputs 6, maximum iteration. This is the most important variable, 6 variables, because here we have 6 number of unknowns. And after that we compile it. We'll go to the Simulink model. Insert is function block. And define and save this model on desktop. We'll bring this to where we save our model, and choose this function. Here is H, C, A, XL, XH, and B. This is for equality constraint. Now the output, we can display it on display. We go to Things, and choose Display. Okay, we'll configure our model. We'll put 2 seconds or 1 second. Variable fixed step, range quota 4, and here 0.1. We run. Optimal value of X, the same results. In this part of the video, we are going to do the same thing in Python, and you will see how straightforward it is with qpsolvers library. First, we can install qpsolvers by pip install qpsolvers. And after that, I have opened Jupyter Notebook, import NumPy library for vector matrices, and from qpsolvers I imported solve_qp. We are solving a 6-variable optimization problem. The objective function we want to maximize is this. Now, quadratic programming solvers usually minimize functions of the form from 1/2 x transpose x hx plus G transpose X. So instead of maximizing J, we will minimize negative j. In the code, we start by defining Hessian matrix. And the gradient vector g. The quadratic terms for x3 and x4 go into h, while the linear coefficients for negative j go into g. Next, we add the equality constraints. These are relationships between the variables like x3 equal 0.8 x1 plus 0.44 x2, and similar ones for x4, x5, and x6. We encode these into the matrix A with both lower and upper bounds set to 0 to enforce equality. Then we set bounds for each variable. For example, x3 has an upper bound of 24,000, x4 has 2,000, and x5 has 6,000. The rest are either non-negative or unbounded above. With everything defined, we call solve QP from the qpsolver library. Using OSQP solver, this gives us the optimal solution vector for x1 through x6. Finally, we print the solution and compute the maximized objective j. This shows us the best values of the variables and the maximum value of our objective function. Now there are some difference in the optimal solution. We can minimize the error by using these options in the QP and solve QP by setting the absolute error to 1 e minus 10 and relative error to 1 e minus 10 minus 8. Pardon. Maximum iteration, we can control it. Also, we'll print the values. Now the same values we obtained also from MATLAB. If you watched my MATLAB example, you'll notice the structure is very similar. Both require Hessian, gradient, constraints, and bounds. The main difference is syntax. MATLAB uses qpOASES directly, while Python lets us choose from several solvers through qpsolvers. We can use another solver by installing it. Pip install CVXOPT. We can use this solver. Now we go to our code, Python code, and use this solver. Here we use CVXOPT. We run the program and get the same results. Also, we can use OSQP directly by importing it, and here we change this line OSQP dot QSQP, and we set the problem tolerance and solve it. The results in X, and we get the same results. And that's it. We have solved a 6-variable quadratic programming problem in Python. If you want to try it yourself, you just install qpsolvers and CVXOPT with pip. Experiment with different solvers or modify the constraints to see how the solution changes. Thanks for watching, and I will see you in the next video.